Okay, so looking at integer types, you could do basic integer operations on them, and certain operations will give you a float type. So if you type of 5, it says it's an integer, type 5 divided by 5, which gives you 1.0, it'll give you a float. And float means you have a floating decimal that moves around. So it's represented differently in memory, and floats don't have infinite precision. So they just approximate certain ratios. Like if you did square root 2, it doesn't give you all the decimals. It has a sort of maximum precision. So it's useful for certain computations, but just know they're not safe for things that require high precision. And similarly, like if you look at like other operators that support integers, you could do 5 to the power of 5. Two of these mean to the power of, and yeah, you can build up pretty big numbers pretty quick, as you can see. And as you'll notice, it'll just keep growing. Unlike other systems which have a maximum and a minimum size an integer can be, Python will just spit it out, or at least die trying. It's a very big number. So these are integral types. All sort of number-based types are derived from integral types. And interestingly enough, even though we went through booleans and we treat them as something that could have only 2 values, they get cast. Cast means converted to a different type if you mix it with other integral types like number 5. So treat true as a 1. In fact, you could cast it directly using the int built-in keyword, and you can do the same with booleans. With false. So booleans are also based off this integral type, which is sort of built into the standard library. So they have floats, integers, booleans. Those are all integral types. And there's also other ones for other forms of numerical computation, like complex numbers and fractions, but we won't get into that. But the standard library in Python is enormous, and it's there if you need it. So some of the cool operators, if you say, okay, I want to bind x to 5, there's some shorthand operators which will let you do cool tricks with it and modify it. So instead of doing x is equal to x plus 5, which will say, x is 5, and plug it in here, you get 5 plus 5, x is 10. You can use a shorthand like plus equal to. Say get the value of x, add it to 10, and put it back in x. So as you can imagine, there's minus equal to, there's times equal to, there's divided equal to. There's also the integer divide operator. So if you did 5 divided by 2, gives you 2.5. If you did this operator, it would truncate down or take the floor. So it would disregard this fraction completely and just give you the integer without the fraction. And so you can imagine that what this would do. This divides it and it only keeps the integer essentially. X divided equal to 2. Oh, it's not supposed to do that. Well, I guess since it was already a floating point, it cast it. But this tries to keep it. Yeah, so what it's doing is saying x is equal to, let's say, 18.0 divided by 2. This will, it doesn't matter if this is saying only keep the integer, because if you have a float, it's going to automatically put the other one as a float. It's going to be sort of changing types, and changing types is called polymorphism. We'll get into that. But if you did it this way, yeah, that truncates it down. Yeah, so that's just something to be mindful of. So those are some of the operations you could do with numbers. The next built-in type we're looking at. So all the built-in types we've looked at so far, they're sort of hold one value. So the next one holds sort of a sequence of values. And anytime you talk about holding more than one value in Python terms, these are known as collections. And there's sequential collections or sequences. There's non-sequential ones. Unordered, we could call them, or non-sequence, whatever is the proper term. So there's sort of two types of strings in Python that you'll most frequently encounter, and that's just Unicode sequences. So this is a sentence in Unicode. So in Python 2, the Unicode support was not built in. So what that meant was in most programming languages that are a bit older, each character is an ASCII value. So there's a byte value from 0 to 255, which represents the character. And so you can imagine in Python 2, this would be the ASCII value of t, which is some number from 0 to 255, the ASCII value of h, of lowercase h, in a sequence. So in memory, it's contiguous, so it's in order. And that allows for quick access to different elements of the sequence. The fact that it's in order makes it very fast to access in memory. So the amount of time it takes to access this element from this whole sequence is equal to the amount of time it takes to access that if it's contiguous in memory. So some of the cool things you could do with strings, obviously, is print them out. And to sort of fortify that it's Unicode, we can get an actual Unicode symbol here. There we go. And just append it there. So this will build a new string from two strings. And append means add to the end of, adding the I love Unicode. And since my shell supports Unicode, I could see the heart here too. So Unicode supports more than 255 numbers per character. It's like up to, I'm not really sure if it's more, but I thought it's 65,000 something. So some other stuff you could do with strings is access elements. So all ordered, all sequences in Python can be accessed with these brackets. So if you want to access the first element, you'd put a 0. And that would give you the big capital T here. If you want to access the next element, you do x of 1. That would give you the H. So another cool thing you could do with strings and other collections, and I think this applies to uh, a large majority of the collections, I'm not going to say all, is the length operator, len. It's a built-in, which tells you how many items you have in your collection. So it says 18. So basically, if I want to access the last element, I'd have to go to the 17th index in order to get this E right here. Oops, I put square brackets there. That gives you the last element, and that gives you the E. Another way to write it is if you get a length of x and you subtract 1, 18 minus 1 gives you 17, it will give you the last element. This is typically how in many programming languages you get the last element, but Python has sort of something built in that's, I'm going to copy and paste this line, that sort of shorthands that. If you get rid of this length completely, just leave a -1, it's smart enough to say you want to go the other way. So just imagine it goes from the 0 all the way to the end, just gives you this last element, and that will just give you the last letter or last element of a sequence, second to last, etc. So it's just kind of a cool little trick. You can do other stuff with strings. So if I just want to get the first word, there's a few ways I could do it. So I could do x from basically 0 to 0, 1, 2, 3. So this notation here is known as a slice. It's if you have a sequence, you can get subsets of it, and they're called slices. And slices are their own object in Python as well. And the way it works is so the lower bound here is inclusive, so it will start with 0. This upper bound is exclusive, so it will not go to the 4th index. It will go up to the 4th but not include it. So that's why if you want to get all the way up to this S right here, 0, 1, 2, 3, you have to put 4. So say go up to this but don't include it. So it'll only give you this word. And that's why if you put a 3 here, you'll miss that last letter. So it'll only give you 3 elements instead of 4 is what you want. You want to get 4 elements from 0. Another way to think about that is if you have 0, 1, 2, 3, that's 4 elements. So if you want to get the number of elements typically in program, you just say the start index plus num elements minus 1. So 0 plus 4 elements minus 1 is 3 elements, or the third index. So it's just a way to think about it. So if you want to access all the way to the end, so there's this idea of default values in Python. And if you don't put anything after, it assumes you want to go all the way to the end. Because the default value is sort of the idea of this length of x minus 1. So it's like the default value here is like a -1, which is shorthand for length of x minus 1. So you could leave that out, and it will already go to the end. This is a sentence. Likewise, the default value for the start is a 0, and you can leave that out as well. However, this will return to the whole string to you. But there's this idea of immutability, which we'll discuss in our next data structure that we go over, built-in data structure, where this gives you the whole thing, but it actually does something a little different. So just keep that in mind when you see this. This gives you the whole thing, but for mutable data structures, which I'll explain what they are, it does something different. So if I wanted to get from, let's say, the H here to, let's say, this C here, so the second element to the second to last, and skip every other one. Oh, first let's just do the subset. So this will give you a nice clean subset, starting from the H all the way up to the, oh, it went up to the, didn't include that. So if you do -1, that will include the C, yeah. So it's actually slightly different than what I said. This -1 means essentially go up to this E, but don't include it. So that's what the slice is doing, because this, remember, is not inclusive. So that gives you a subset, sort of getting rid of the outer characters. And it has one more thing you could, so if you wanted a smaller subset, you could do this, obviously, give you less. If, let's say, you said, okay, I want to start with this I here. I want to go up to n, which is this -2, because this is -1, this is -2, and it's not included. So go to the n. But you don't want to go in order. You don't want to step through these one at a time in the sequence. You want to step through them, let's say, 2 at a time. So this is lower bound, upper bound, not inclusive, step. That's how slices work. So it's skipping the characters. So in order to clean this up so you could read it better, I'm just going to use this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good enough. So I'm putting a string literal here. Instead of saying x equals this and putting x here, you can just put a literal string, and it'll be accessible with this slice. So what this will do is it starts from the second element, 0, 1, 2, includes it. It'll go to the second to last, 8, up to that, not included, so the 7. So it's from 2 to 7, skipping by 2. So 2, 4, and 6 will be included. That's where we get 2, 4, and 6. So that's what slices do. And there's also this cool little added bonus. If you put a -1 step here, it will go backwards through the entire thing. So you could think about it as it will get the 2 and up to the 7, or up to the 6, because it's not including that. Since it's a negative, it'll flip the whole thing, and then it'll step through it one at a time. Did I make a mistake? Did I not save it? Maybe. Let me try that here. That goes backwards. 0. Yeah, I guess the canonical form is, so probably a better way to do that. I'm not sure what exactly the thing is, the problem is, but if you get this subset here, you can reverse it like so. So, for example, you could apply this step later. Maybe I'm not completely understanding the semantics of the slice, but if you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say you get the subset from the first element, so to the second to last. You can reverse that by putting a negative step afterwards. And that's a negative step of 2, negative step of 3. So that's a way to, that's how slices work in sequences. And that's strings. Of course, there's many other operations you can do on strings. It has a lot of cool built-in things. So initially, we want to get this word, the word this from this x. You could actually do x dot split and space. This will lead us up to our next data structure. So, sorry, I ran the wrong thing. As you can see, it returns something that has these brackets here, and it has 4 items, which are all strings, 4 elements. This is a list. It's another built-in type. It's the next built-in type we're looking at. And it's also ordered, but it's the first immutable type. So I'll explain what that means in a second. But since it's ordered, you can access the word this directly. So what I mean is the first element is accessed by the 0, index of 0. It'll give you this. Oops. So what we did here is we got the whole, this is a sentence, we split it by space, the character space. So what it does, it says every time it sees a space, it so the first time it sees a space, it says, okay, I got my first element, which is at this. And then it goes and says is another space, I got my second element. So it builds a list from a string full of elements of that string. So it's a nice way to split up a data structure. So if you had a bunch of sentences, this is another sentence. You could actually use a dot, which is known as a this right here is a period delimiter. This is a space delimiter. Delimiter is how you separate things in a string. So now I got the first element, which is this is a sentence, because the delimiter is a dot this time. So yeah, that's pretty much strings. And let's go explore lists a bit. So these are strings. These are integers, part of the integral types. Yeah, these were booleans. This is the none type. So let me show you one more example with strings. So if you had a string that just hello, you got the ID of that, it gives you some address. It says, okay, hello is at some address in memory. And if you modified x and said x is equal to x plus, this is a way to do string concatenation to add strings together. So X is now hello world. So something changed. If you do ID of X, as you can see, it's not the same ID as it was before. This is because strings are immutable. So if you want a new string, it takes a previous string and creates a new one from the operations on the previous data and the new data. So it's in a different memory location. So you can't modify the original X because X only referred to that object, and that object is not changeable, it's immutable. Same with numbers. You can't, it's just like, it doesn't make sense to modify. So X plus 5. And if you did X is equal to X plus 5 again, ID of X, it's a different memory location. That's because from Python's standpoint, it doesn't make sense to modify certain objects. And numbers, like the number 5, you can't modify number 5. The number 5 is number 5. All you can do is point to the number 5. Same with strings. The string hello is a string hello. You can't modify the string hello, that's what it is. The same is not true for lists. So if you want to make a list, this is the first mutable data type we're going to be looking at. You started with an open and closed square bracket, and you could put any object as its element. So you could put none, true, false, hello, 5, 13 plus 4, and you could also put other lists, 1, 2, 3. You can nest them as deep as you'd like. That's what a list is. A list is mutable, so if you were to make a change to a list, you did mylist.append, so let's say print my list. So it prints out the whole thing, and we appended hello world, which append means add to the end. So if we say ID of my list, it'll also print out the memory location. It's a memory location of that list, and this is all the contents of it. If we modified it again, let's say we want to add 2 to the power of 10 at the end of it, and print my list, print ID my list. Also, just for clarity's sake, print type my list. Type gives you the name of the type. So if you run this again, see, we modified it here, and yet the memory address is still the same. That's because it's mutable. So the object was changed. And here it says class list. So that's a type. That's how mutable types work. The object can change. So the issue is if I said my list2 is equal to my list, and then I did my list.append something else. So what do you think will happen here? Well, my list2 and my list are both pointing at the same object in memory. You add something else, this string literal to the end, so my list, the object that my list is pointing to changes and mutates, and since my list2 is pointing to the same object, it also changes. So you have a side effect. Something else is here in my list2. This is one of the dangers of having a mutable data type, because you changed this variable You did not expect to change this, and yet this changed. So that's why it's often preferred to use immutable types, but it comes at the cost of performance in certain cases. So what I think was meant, what you meant to do, remember this operator I said earlier to remember? If you do this, it gives you the entire list, but for mutable types, it copies it. For mutable types, this list will be copied. Now that's pretty handy, because now if you run it, something else is not there, because it copied the entire list. So there's a new object that mylist2 pointed to with the same contents, but a different memory address. So if you say print id mylist, the memory address of that, id mylist2, these will have different memory addresses because they're pointing to different objects. There you go. So that's what mutability introduces, complications like that. But it comes at you gain flexibility. So let's say you want to merge lists. You have list 1 is equal to 1, 2, 3. List 2 is equal to 3, 4, 5. The same way you concatenate strings. You say list 1 plus list 2. Print list 3. And it merges them. You can apply slices to on lists since they're ordered. So you list 3. Okay, I want this from the second item to the second to last, skipping by 2s, whatever. And print that out. So there you go. It starts from the second item, including it, goes to the second to last, and skips by 2. So I guess this 2, guess this 3, I can't go anymore. So there you go. There you got slices with lists. So lists are also very useful for iterating through. So if you want to do processing on each individual element of the list, so let's say you have list 3, which is the merging of both lists, and you want to iterate through all the elements, you can use a loop called a for loop, which will help you iterate through all the objects. And just like the if statement ends in a colon, and just like the if statement has a block spaced by 4, where you put the processing in. So in this case, if you want to, let's say, get all the numbers of that element and add square it or something. Let's say we want to print both. The print statement allows you to print multiple things by just putting a comma. So here it is, 1, 1, 2, 4. It's printing the squares of each of these elements. So yeah, you could explore more on loops, but I just want to go over the rest of the data types. So if you want something like a list that's not mutable, you can use a tuple. There's a built-in type called a tuple. And or to make a tuple, it's similar to making a list. Use parentheses though. And so this is a sort of less flexible list because it's immutable, but it's sort of safer since it's immutable. there's some cool stuff you could do with tuples called tuple unpacking, which I want to show you. Here's a tuple. You type tuple3, say it's a tuple. So that's merging tuples. So something you could do with tuples, which is you could do with any ordered sequence that's finite. Well, you might be able to do with some infinite lists, I'm not sure. But let's say you had latitude, longitude equal to 34.123 minus 74 point, some location on the Earth, lat long. So lat long is equal to that tuple. That's kind of cool. You could access elements of latitude, longitude with indexes. Like that, just like lists. But by having unpacking, the ability to unpack, you could sort of do more interesting things with them. So instead of writing it like this, you could actually say lat1, lat or launch 1 is equal to say 32 point whatever minus 70. This will unpack the variables. So this variable will go to lat1, this variable will go to launch1. And that's sort of a nice way to break data apart. There you go, it's printing those two out. This is pretty useful if you have a lot of data. So let's say you just want a latitude in this case and other data. So let's say you had latitude, longitude, and also altitude in meters or something. What this does is says unpack this, but I want the first element to be unpacked to latitude 1, all the other elements to be unpacked to other data. And this star here just means this is going to be a list. It's going to be another list or another sequence. I mean a tuple in this case. So this is sort of like throwaway data. So if you run that, get your latitude, and oh, I guess it does cast it to a list. That's interesting. So since it's throwaway data, it's actually conventional to use the underscore because, I mean, unless it's not throwaway data, but in this case, I'm just saying you don't need it for this context. So it's just a convention to use underscore. So that's tuple unpacking. So let me show you this thing called zip, which is a built-in function working on ordered sequences like lists. So let's say you had this list and this list, L1, L2. So if you wanted to make it so you make a new list from these two where 1 and A become a tuple, 2 and B become a tuple, and 3 and C become a tuple in a list, you can use zip. Let's see why this is useful. Let me cast it to a list because it's lazy. So as you can see, just like the, on your jacket, if you have a zipper, it just like combines both sides of the sequential chain. That's what this does. So if you could visually imagine you have a list on one side of your zipper, a list on the other, that's what the zip function does. It just puts them together as elements. So that's useful in a lot of cases. So for example, let's say, let me kind of work around this. Let's say you had the numbers, let's say you want to go through a loop through L2. So all the elements in L2, you want to print them. So you want to just see what the elements were first. And there you go, you got your elements. But let's say you also want to know what the index was of each element. You could use tuple unpacking in this for statement. If only this, if each element of this was a tuple. Well, you could totally make it a tuple by using zip. So, oops, I meant to type in elements here. Element. Sorry if that caused confusion. So let me just rerun this just to get clarity. So yeah, it prints ABC, but let's say you want to print the index and then the letter. So like the 0th element is A, the first element is B. You can use zip here. Say zip L1, L2. And the elements will be tuples. And you can also unpack them. So you can say index letter, which is the actual element. So index letter. And see it unpacked per iteration. So this is kind of cool way to, in a loop, know what index you're on. But instead of using zip and having to sort of generate these, by the way, this was not correct because this is supposed to be 0th index. So it's supposed to be 0 here. 1, 2. So yeah, instead of using zip and sort of having to, combine it with this array of indexes, there's a built-in function called enumerate, which already does the zip for you in the background. It generates a sequential ordered set of integers that are the same length as this, and then it zips it. So it's super useful for getting the index. And this is useful for many times when you're going through loops and you need to know what index you're on and compare it with other parts of the list index.